homework. Number one, homework, you have 256 to the 3/4 power. We're just going to reduce it. You guys keep it down?
Yes.
Okay, keep it down. So 256, that's 2 to the, here's the 8th power, right? To the 8th power, to the 3/4. The power to the power, so you multiply them together. So you have 2 to the 8 times 3/4. The 4 and the 8 reduce, give you 2/1. So that's 2 to the 6th power, which is what? 2, 4, 8, 16, 32, 64. So number one, the answer is 64. All right. Any questions about that? Number 8, w to the t r to the -1. Anytime you see a negative exponent, you should always try to get rid of that first. It kind of makes your life a little easier. So when I get rid of that negative, I have w raised to the t 1/r. Now r to the -1 becomes 1/r, because anytime you have a negative exponent, the base is going to flip. So that's really just w to the t/r. That's pretty much all we can do. All right, we put it as a radical. We'll get the r root of w t. Yeah.
Wouldn't that also be w to the t power over w to the r power?
W to the t power. See ya?
W to the t power over w to the r power.
No, because it's not w to the t to the r. It's w to the t times r. Is that what you're asking?
Like, if it's w to the t to the r to the negative 1, it would be w to the t.
No, but this is w to the t times r to the negative 1. Did you think it was w to the t to the r to the negative 1?
No, like, does the r to the negative 1 not apply to the w?
No, the negative 1 only applies to the r. So it's like one of those power towers. We don't really do that, talk about that long in class. But it's the power is only related to it only has one base. So the negative 1 is only related to the r, not the w.
How do you know whether to put it in fraction form or in the radical form?
We'll tell you to put it in radical form. I think on the quiz, that big of a deal. On the quiz, we're going to tell you, yeah, in the quiz, we're going to tell you to put it in radical form.
All of them?
Yeah, so the quiz, we're going to say reduce it down, put it in radical form, so you want it in this form. All right? Any other questions? Are we okay? All right, number 32. So we have the square root of 12 minus 5 root 6 to the 26th power. So it is an even power. So I want to figure out, well, is 12 minus 5 root 6, is that an even or a negative number? Right? I know the value of 12. I know the value of 5 root 6. I know their actual numbers. So I can figure out if this is going to be a negative or a positive number, and if I need absolute value or not. So 12, that's the same thing as the square root of 144. 5 root 6, that's the same thing as the square root of 5 squared times 6, or 25 times 6, which is 150. So 5 root 6 is the square root of 150. 12 is the square root of 144. So that tells me 5 root 6 is bigger than 12. So that's why 12 minus 5 root 6 is a negative number. And anytime you get a negative number, and you have an even exponent, all you really have to do is just flip the numbers. You need to, so you don't have to deal with the negative. Because now I flip this, the value is actually the same. The value didn't change. So if it was an odd number, you couldn't do this. Like an odd power, you mean?
Yeah.
If it was an odd power, you couldn't do it, because what's really happening here is that when you take out the negative from the beginning, you flip it, you have negative of 5 root 6 minus 12, all up to the 26th power.
Oh, so you just simplify it.
Yeah, because you get negative 1 to the 26 to the 5 root 6 minus 12 to the 26, so that's the same thing. And then this is just 1. This negative 1 to 26 is just 1. It kind of just goes away. So really, if it's an even power, you can really just say, well, 5 root 6 is bigger than 12. All I really need to do is flip the numbers. and it's the same exact thing. Right? This is like getting 1 or negative 1. Right? 3 minus 2 is 1, but 2 minus 3 is negative 1. If you square both of those, you get the same. It's the same thing. And then from here, it's a square root, so it's a 2. So what you get is 5 root 6 minus 12 to the 13th power. Don't extend it out, that's going to be your answer. Any questions about that? We good? Okay.
So there's that one rule with like the absolute value that doesn't apply to go from odd to even.
No, it's even to odd. Always even to odd. Because the reason why is because evens will always give you a positive number, right? Anything raised to an even power is always positive, right? But anything to an odd power won't always be positive. So if you have an even exponent, like let's say we started with like x to the 4th, let's do like the square root of x to the 4th. Very kind of on the side, right? Okay, the square root of x to the 4th, or it's just x to the 6th. Well, if you reduce that, that's just x to the 3rd, right? Well, how does he plug in negative 1? It's not the same. If you put an absolute value around it, now it's the same. Because here, for x, you don't know what x can be. X can be an infinite amount of things. It can be negative 1, 1, 2, negative 2. It can be a negative or a positive number, right? Because we don't know the value of x, you have to account for every single case by saying, well, x could be a negative number, so you need to put an absolute value to make sure it stays positive. But in this case here, see in the very beginning, 12 minus 5 root 6, that's a negative number, right? So here, I know the value, this is not going to change. It's always going to be negative. So I'm like, well, I can just flip it and change the value to make it positive, so I don't need an absolute value. Because 5 root 6 minus 12, that's a positive number, right? Because 5 root 6 is bigger than 12. So there's no variable here to change the value. It has a set value. Well, x can be anything, so it's like you have to account for all the infinite cases and say, well, we're going to put some absolute value signs around it.
Oh, so because it's a negative number to the 26th power, it'll come out as positive, and then the number down there.
Yeah, so if I didn't fix it and I left it as 12 minus 5 root 6 to the 13th power, this would be a negative number, right?
Yeah.
But this is the beginning, this is a positive number.
Yeah.
So this will be absolute values, but also, because we know the value here, we can actually mess with it and say, well, I don't even need the absolute values, I can just mess with it inside and fix it. Does that make sense?
Yeah.
That
What if you put the absolute value on the inside, but it's still correct? Like say the absolute value of 5 root 6 minus 12 to the power of 13. And 12 minus
it depends. It depends on I think it doesn't matter, but I'll have to think about it for a bit. I'll get back to you on
You
that.
guys see points off.
This is the absolute values.
No, like we put the absolute value in switch.
You can take it to the outside.
Yeah.
Yeah, that one, nothing that ambiguous is going to make this. Don't worry about that. But I'll think about that later. He did. We honestly, in this case, we would, because that's kind of what we're testing, and also at the same time, it's not fully simplified. We're saying simplified radicals. So if you gave me this, that's not fully simplified.
And also, do you apply absolute values to everything that goes from anything between what changes from negative positive to odd?
Only evens to odds. It's absolute values. You're pretty much saying it needs to stay positive, and that's why you start from even to a positive, even to an odd. Sorry, because an even power always gives you a positive number. One odd can give you positive or negative. You're not sure. So to make sure it stays the same sign, you put absolute values around even, from evens to odds. Any other questions? Are we okay? Odd to even? What do you mean? Odd to even? Because the thing is, like, if it's an odd power, you don't know what the base can be. If it's like an x to the 3rd power, you don't know what that can be, so you don't put absolute values because it doesn't mean that. All right, number 39. So what I'll do here is I'll simplify what's happening inside the parentheses first, and then work with the exponents, right? So I have x to the 3 over 8 times y to the 3 over 10 over y to the negative 2 over 5 x to the 5 over 4. All that raised to the negative 3 over 7. So what I would do is I would combine the x's and y's inside the parentheses first. So it's x to the 3/8 and it's x to the 5/4. I can combine those, where I can subtract this being divided, you can subtract them. You can rewrite this. We're rewrite the x's anyway. Say it's x to the 3/8 minus 5/4. The y, same thing. That negative 2/5, you move it to the top to get y to the 3/10 plus 2/5. Everyone with me? Right? Because if it's top and bottom, you're subtracting them. Because if you have x to the 3/8,
Oh, I understand.
right? To move to the other side, you can just say, well, it's x to the 3/8 times x to the negative 5/4.
Yeah.
Right. That's why. So what you get here, x to the 3 minus 8 minus 5/4, that ends up giving you x to the negative 7/10, and the y gives you 7/10. Right? So 7/8. 7/8. All right, and this is all raised to negative 3/7. So from here, distribute the negative 3/7 to each power. So for the first one, you get x to the positive 3/8. And for the second one, you get y to the negative 3/10. You don't want a negative exponent, so you just put the y to the bottom. You get x to the 3/8 over y to the 3/10. Any questions here? What?
If it was y to the power of 3/8, can you combine the x and y?
So if you're saying those like x to the 3/8 over y to the 3/8?
Yeah. Or times y to the 3/8.
Like this? Yeah. I mean, you can. If you know what x and y is, you could. You can rewrite this as x times y all to the 3/8. And you could do something like that, like if I had something like 2 to the 3/4 times 3 to the 3/4, that's just 6 to the 3/4. You can do that.
So wouldn't that just be y over 2 r?
Which one?
The first question we did.
No, because it's one base. It's t times r.
Yeah, but then that's the same thing we did there. That's t minus 1. Oh, alright.
You got it? You could. I mean, this is the way I did it. You can do it many different ways. If you wanted to flip it from the very beginning, you could. It doesn't matter. As long as you're applying the rules like in the right way, you could have done it, a bunch of different ways. So if you want to flip it first, that's fine. Any other questions? All right, number 44. So this one, the first thing I'm going to do is rewrite it into a prime factorization. So the fourth root, 64 is 2 to the 6. X to the 18. Y to the 36. So from here, what I'm going to do is I'm going to take each exponent, divide it by the root, and figure out what you have. So 6 divided by 4 is 1 with a remainder of 2. So you can factor out 1, 2. And I'm left with a remainder of 2, so the exponent stays there. X to 18. 18 divided by 4 is going to be 4 with a remainder of 2. And y to the 36, that just gives you 9. Y to the 9th power. And since for this y, you went from an even exponent to an odd one, that y needs absolute values. Everyone with me so far? Good. Because from the very beginning, if y was -1, what's -1 to the 36th power? 1. How about -1 to the 9th power? See how the value changed? Because the value changed, you have to put an absolute value.
Okay, so only when it's even to odd.
Yeah, even to odd, you put absolute values.
Also, why do you know when it's odd?
Because when it's odd, your value can be either positive or negative, right? And then if you reduce it down to a positive, all that, or to an even, all that means that well, it has to be an even number. It's like, right, I think about it, it's like give the square root of x to the 6. What do you get for that? X to the third. So in this first answer, if x was -1, you get the answer of 1, right? For the second one, you get -1. So you have to put absolute values here. So if you did something like, let's do 4th root of x to the, what's the on the 15. What's the number that gives you ought to even? Second root.
Is it even one of those?
Like, x to the 15 and the root of that.
Ought to even. Is there anything? I think you can go ought to even.
Why do you not answer that?
Oh, that hasn't got it yet. Right, we haven't finished this problem yet. I don't know if you can go ought to even.
Well, that's impossible.
I think so.
Yeah, it doesn't make sense.
I think you can go ought to even. Alright. That's one. Alright, so from here, this 4th root of 2 squared x squared, if you actually reduce this, because all the exponents in the roots are all divisible by 2, you can divide them all by 2 to just get the square root of 2x.
Why didn't you divide them up?
So the reason you can do that is because this 2 squared, x squared, is the 1/4, right? The 4th root is all that, right?
Yeah.
So that 2, I can factor out a 2 to get 2x to the 2/4. So basically what I'm doing when I'm reducing the exponents in the root is just a faster way of just reducing down the numerator and the denominator.
Yeah.
Right? Because the exponents is your numerator, the root is your denominator. You could just flip it and put it back, it's fine. Any questions about that? And now the x needs an absolute value because it's raised to the power of 1, but it started with a power of 18. And that's going to be 2 x to the 4th y to the 9th power. Any questions about that? All right. Yeah.
Just to be clear, you don't need an absolute value around the 2 outside because you already know it's positive.
Exactly. 2 is already positive. There's no point in an absolute value because you already know the value. All right, number 47. At the 4th root times the cube root of 3 all over the 6th root of 6. So same thing. Anytime you have all these numbers, you want to reduce it. Put it into its prime factorization. So in this case, you have the 4th root of 2. Let's put 2 squared times the 3rd root of 3 all over the 6th root of 2 times 3. Right, so put all the numbers into your prime factorization. And they're going to rewrite these as fractions or as exponents. So 2 to the 2/4 times 3 to the 1/3 all over 2 to the 1/6 times 3 to the 1/6. Which one? Where?
It's just 2 to the power of 3, right?
No, it's 2 times 3. 2 to 6. Sorry, my hand already got it. Right, this is what you get. And then you start combining the similar bases. So 2 to the 4th, or 2/4, that's just 1/2. So you can rewrite this as 2 to the 3/6 times 3 to the 2/6 all over 2 to the 1/6 times 3 to the 1/6. Combine these. And 3/6 over 1/6 reduces to 2/6. You get 3 to the 1/6. I don't want to have 2 different roots happening, so I'm going to leave 2 to the 2/6 as it is. Because I want to have it all underneath one root, which would be the 6th root of 2 squared times 3, which is the 6th root as well. I don't ever want to see a root times another root, so that's why I'm leaving it the 2 to the 2/6. I'm leaving it like that because I want them both underneath the same root. What?
So, like, what kind of numbers? Should we expect expect like these numbers on the
Yeah, the quiz, we're not using a calculator. The numbers should be relatively small. We're gonna try to keep everything in bases of 2s, 3s, and 5s. Like we're not gonna have anything in bases of 7. I don't think so. And if it was, it would be like 49 or easy numbers. All right, so we're not trying to kill you with algebra. Just it's gonna be simple bases. Any other questions? Are we okay? All right, number 48. So the second root of 10 times the fourth root of 20 times the eighth root of 50. So we're going to treat this pretty similar to the last problem. Put everything into its prime factorization. The square root of 10 is 2 times 5. 20 is 4 times 5, or 2 squared times 5. And 50 is 25 times 2, or 5 squared times 2. So put it into its prime factorization. And then we can put it in exponents to combine them together. So 2 to the 2 fourth, or 1/2, times 5 to the 1/4, times 5 to the 2/8, which is 1/4, and 2 to the 1/8. Right? So you've got our prime factorization of everything. We put them into exponents. And now everything's in bases of 2s and 5s. So you can combine all the 2s. So you have 2 to the 1/2 times 2 to the 1/2 again, times 2 to the 1/8. And we do the same thing with the 5s. 5 to the 1/2 times 5 to the 1/4 times another 5 to the 1/4. So we're multiplying all the bases of 2, so you add the exponents. So that ends up giving you 1/2, or 1 plus 8 gives you 9/8. And then for the y's, you have 5. That ends up being 2/4 is 5 by itself, 5 to the first power. So 2 to the 9/8 is just 2 times 2 to the 1/8 times 5, which is 10, the 8th root of 2. That's going to be your answer. Any questions about that? Are we good?
So we're simplifying the most.
Yeah, we're simplifying as much as we can and then putting it to radical form. All right, for this one, we're going to multiply these together. So just FOIL it out. Distribute the root 2. You get root 2 plus the square root of 2 times the cube root of 4. Distribute the cube root of 2. Get the cube root of 2 plus the cube root of 8. Right, so FOIL it out. The square root of 2 is just the square root of 2. I can't do anything with it yet. This root 2 and this cube root of 4, I don't ever want to see a root times a root. You don't want to see that. So we need to combine them together somehow. So what I'm going to do is I'm going to rewrite them into their prime factorizations. So 4 is 2 squared. And then as a cube root of 2, and the cube root of 8 is just 2. So this square root of 2 times the cube root of 2 squared. I can rewrite them as fractions to get 2 to the 1/2 times 2 to the 2/3 plus the cube root of 2 plus 2. So from here, there's 2 to the 1/2 and 2 to the 2/3. They have the same base, so I can combine them. So 2/3 is the same as 4/6, and 1/2 is the same as 3/6. So what I have is the square root of 2 plus 2 to the 7/6 and then 2 to the 7/6, the square root of 2 plus 2 times the 6th root of 2 plus the cube root of 2 plus 2. Yeah, that's what I'm double checking. That's really all you can do.
Is it?
Yeah.
Can't you make 3 over 2 root 2?
Which one?
You can simplify it.
Which one?
2 times root 6 over 2 plus root 9.
So,
That goes to 4.
yeah. You really can't do anything else. This is your final answer. Go ahead.
So when you're multiplying, you use like the basis, right?
What do you mean?
Like when you're multiplying, it's like 4 squared times like 5 squared times 4 to the 8.
Like this?
You only multiply 4 to the 8. You only multiply the 4s, yeah.
Yeah, you can only really combine these two to get 4 to the 10. You gotta kind of think like what do exponents really mean? Exponents just tell you how many of those you have. You have 2 4s, 8 4s. So you multiply them together. What that means is you're multiplying 10 4s together.
So then when you're adding, you go by like what's.
Yeah. So if you have something like 2 square root of 2 plus 3 cube root of 5 minus the square root of 2, these are the same exact root and same thing underneath the root. So remember, you multiply something, it tells you how many of it you have. This says I have 2 root 2s, I have minus root 2s. So what you have is a square root of 2 plus 3 cube root of 5. Does that make sense? Okay.
When you're multiplying cube roots, you're only affecting the thing inside.
What do you mean by multiplying cube roots?
So you have cube root 2 times cube root of 3. Maybe just cube root of 6.
Yeah, right here, cube root of 2 times cube root of 4 gave me cube root of 8. All right, 74. We're going to rationalize this. You rationalize it by multiplying the conjugate. So I know on the bottom, it's a difference of squares. So you get 1 squared minus root 5 squared. On the top, distribute the 3. You get 3 minus 3 root 5. Distribute the negative root 5. Negative root 5 plus 5. The 5 and the 3 on the top gives you an 8. Negative 3 root 5 minus root 5 gives you a negative 4 root 5. And the bottom you have 1 minus 5. So you have 8 minus 4 root 5 all over negative 4. The 3 and the 5. These are all divisible by 4. So divide everything by 4. And you get 2 minus root 5 all over negative 1. So, you know, it's just changing the sign, so it's negative 2 plus root 5. Any questions about that?
Yes, that last step.
Yes. You want to write 1 over negative 1, you just something negative 1, right? Same thing with this. What number is this? 74. Yep. All right. 84. This one's kind of hard. Well, kind of long. So this one I have a negative exponent. So anything with a negative exponent, get rid of it. So we have 1 all over 1 minus root 2 minus root 5. And what you want to do is you want to multiply it by some number that will get rid of, you know, the bottom. So in this case, you're kind of lucky with a trinomial with 2 roots. So that means we're going to have to multiply it by its conjugate, so kind of like its conjugate twice. So I'm going to multiply top and bottom by 1 plus root 2 plus root 5. So the top is pretty easy. It's just 1 plus root 2 plus root 5. Bottom's be a little harder. So 1 times 1 is 1. 1 times root 2 is root 2. 1 times root 5 is root 5. Distribute the negative root 2. Get negative root 2 Negative root 2 times root 2 is a negative 2. Negative root 2 times positive root 5 is negative root 10. Distribute the negative root 5. Negative root 5 times 1 is negative root 5. Then a negative root 10. Then a negative 5.
Can you just get negative 6?
What? In the bottom? Because we have two negative root 10s. So these canceled, and then 1 minus 5 is negative 4. So the top is 1 plus root 2 plus root 5. The bottom, we have 1 minus 2 is negative 1, minus 5 is negative 6, minus 2 root 10.
Why do you have 2
Root 10 here and root 10 there. Because it's given multiplied. So I changed both signs. I think it was Mr. Stevens. He did 1 minus root 2 plus root 5. You try that way. I think it might work out the same, get the same answer. That's the way I did it. From here, you have 1 root in the bottom, so just conjugate that. So negative 6 plus 2 root 10 all over negative 6 plus 2 root 10. So in this case, the bottom's pretty easy, just the difference of squares. You get 36 minus 2 root 10 squared gives you 40. On the top, you have to multiply this out. So distribute the 1, you get negative 6 plus 2 root 10. Distribute the root 2, you get negative 6 root 2 plus 2 root 20. Distribute the root 5, you get negative 6 root 5 plus 2 root 50. Is everyone with me? Are we good? So that 2 root 50, what was we write it actually? So I'm going to reduce this down at negative 6 at 2 root 10 minus 6 root 2. Square root of 20 is just 2 root 5. So you get 4 root 5 minus 6 root 5. And then 2 root 50 is just 5 root 2. So you get 10 square root of 2. And all that over negative 4. So really 2 root 20 became 4 root 5. 2 root 50 became 10 root 2. Everyone with me? Are we okay? All right, so combine like terms. I have negative 6 plus 2 root 10. Negative 6 root 2 and 10 root 2 gives you a positive 4 root 2. 4 root 5, negative 6 root 5 gives you negative 2 root 5. All over negative 4. All these are divisible by negative 2. I'd rather not have a negative in the bottom. So you divide everything by negative 2. That gives you a positive 2. This gives you 3, negative 1, negative 2, and positive 1. To get 3 minus root 10 minus 2 root 2 plus root 5 all over 2.
Can you go over like 1 minus root 2 minus root 5 times
1 might say, very beginning.
Yeah.
I just switched the signs to the square root to multiply them.
Not?
I just switched the signs to the square root to multiply them. You have 1 minus root 2 minus root 5. This is the problem, right? I switched the signs of these and then multiplied it together so that I can just, simplify it. What? Switch the sign of the square of the roots. The roots, the square roots, I switched their signs. So I had negative root 2, negative root 5. So I'm multiplying with positive root 2 and positive root 5 now.
No, I get that, but multiplying now.
Yeah.
I don't get how you got this.
1 times 1 is 1. 1 times root 2 is root 2. 1 times root 5 is root 5. Negative root 2 times 1 is negative root 2. Negative root 2 times positive root 2 is negative 2. Negative root 2 times 5 is negative root 10. Negative root 5 times 1 is negative root 5. Negative root 5 times positive root 2 is negative root 10. Negative root 5 times positive root 5 is negative root 10.
When do you multiply by the
Complex conjugate? Conjugate. The conjugate just really works if it's a binomial, like a binomial with a square root. What you're really trying to do is get rid of the square root of the bar. That's all you're trying to do. So there's some problems we have to do like the other part of the sum of squares or sum of cubes or difference of cubes. That's a homework problem.
What? You have 2 minutes.
Maybe.
It's a chance.
Any questions here? We have homework problems pretty quick. Number 90. So Sally simplified 4 minus square root of 9 all over 2 plus root 3 below by rationalizing. You guys keep it down. All right, that was the terrain. I'm just going to tell you guys to do it. The work is on the key. But basically, I'm going to explain to you really quick. Basically, I'll give you a second. That's 88. All right, this one really quickly. This one you do a lot faster if you realize the top is a difference of squares. At the top, you can rewrite as 2 squared minus the square root of 3 squared. You can rewrite the top that way. So you can see, well, that's a difference of squares. So the top should factor to 2 minus root 3. 2 plus root 3 all over 2 plus root 3. These would cancel to give you 2 minus root 3. Right on time. Good luck on the quiz, guys. This is the problem we're given. That's the problem we're given. So I'm going to explain it. But you're right.
That's the way I would do it.
That's what I was going to